Hello and welcome back. In this video we're going to learn about how differential equations can be used to solve mixing problems. So if A measures the amount of stuff, so it could be a liquid or a gas or a population or things like that are in a compartment where you have some things coming in, some things going out of the compartment, and you want to see how much stuff you have inside of the compartment over time. Well then, the rate at which the amount of stuff in that compartment changes over time is going to be equal to the rate at which stuff is coming in minus the rate at which stuff is going out. Now if you have that as your basic differential equation, you can then try to solve that differential equation to figure out how much amount of stuff is inside of the tank at any given time. So this differential equation models that kind of situation, that kind of scenario, and then solving the differential equation will give you a function that models the amount of stuff in your compartment over time. So here in example 7 we have a big tank that initially contains 1,000 liters of a salt water solution, which has a concentration of 0.01 kilograms of salt per liter. Brine, which just means a solution of salt in water, contains 0.03 kilograms of salt per liter of water and is pouring into the tank at 15 liters per minute. Assume that the solution in the tank is kept well mixed and drains from the tank at 15 liters per minute. So notice first off that the flow rate going into the tank is going to be equal to the flow rate going out of the tank. So at any given time there are going to be 1,000 liters of solution inside of the tank. Well, let's look at all these different parts that are going to walk us through eventually how to figure out the amount of salt in the tank over a period of time. So part A asks how much salt is in the tank initially. Well, it says there's 1,000 liters of solution inside of the tank, and that the concentration inside of the tank, at least initially, is 0.01 kilograms of salt per liter. So if you take the concentration of salt, so 0.01 kilograms of salt per liter, right, per 1 liter, and multiply it by, let's write it times here, 1,000 liters, then we're going to get the number of kilograms of salt in the tank at that initial time. So there you get just 10 kilograms. Notice that the units of liters are canceling and you just get kilograms. Okay, so that's how you can figure out how much salt there is in the tank initially. There are 10 kilograms of salt. It's all mixed in the solution, but there are 10 kilograms altogether. Then it says how many liters of solution in part B, how many liters of solution are in the tank at any given time. Well, it's going to be 1,000 liters, right? That's not changing over time because the incoming flow rate and the outgoing flow rate are the same. Same flow rate in and out. Part C asks, assuming the amount of salt in the tank is A of t, so that's going to represent the amount of salt in the tank, the number of kilograms of salt in the tank at any given time. What is the concentration of salt in the tank at time t? Okay, so here we're given the number of kilograms and we're trying to go from that into concentration. So concentration is going to be here for these units in kilograms per liter. So kilograms per liter. So if we have A of t kilograms of salt, and we want to figure out how many kilograms of salt per liter, we would have to take A of t and divide it by the number of liters in the tank at any given time, which is 1,000. So this is going to be A of t over 1,000. Notice that this is in kilograms per liter. That's the units of concentration that we're interested in here. So we have A of t over 1,000 kilograms of solution per liter, or sorry, kilograms of salt per liter of solution. Then D asks, what is the rate at which salt is entering the tank? So this is the incoming rate. Well, the rate at which salt is entering the tank, which we're going to write rate in. There, you're going to be thinking, how many kilograms of salt are entering the tank every minute? That's what it's asking for here. What is the rate at which salt is entering into the tank is asking how many kilograms of salt are entering the tank every minute. Why minutes? Because it seems like our units here for time are in minutes. Well, we can take the concentration of the incoming solution, which we're told, let me jump up here, which we're told is 0.03 kilograms of salt per liter. We can take that concentration of salt for the incoming solution and multiply it by the flow rate. So multiply by the number of liters that are coming in per minute. There the liters would cancel and we would just get left over kilograms per minute. So essentially you're going to take the flow rate, sorry, the concentration, 0.03 kilograms per liter, and multiply it by the flow rate, which is 15 liters per minute. The liters will cancel, and you'll end up getting 0.45 kilograms per minute. So in other words, every minute that passes, 0.45 kilograms of salt are going into the tank. Part E asks, what is the rate at which salt is leaving the tank? In other words, what's the rate going out? What's the outgoing rate? Well, here we have to think about what is the concentration of salt in the tank. And that's changing over time because there's some concentration that's a constant concentration of the solution going into the tank, but then that's getting mixed around inside the tank. And so when the concentrations are different, the initial concentration inside the tank is 0.1 kilograms per liter, and then coming into the tank, that's going to be 0.03 kilograms per liter. So when the concentrations are different, you can imagine that the concentration in the tank is slowly going to go up as the incoming solution is raising the concentration of the solution inside the tank. So it's going to be, in fact, just a long story short, it's going to be changing over time, right? So what we could do to figure out the outgoing rate, what is that, how much salt is leaving the tank per minute, is we can take the concentration of salt at any given time, T, which we actually figured out right here. That's going to be A of T over 1,000. That's the concentration of salt in the tank at time T. And multiply that by the outgoing flow rate. So here I'm going to write A of T over 1,000 times the outgoing flow rate. This is going to be 15 liters per 1 minute. And just let me write the units here. This is kilograms per 1,000 liters. Now once again, the liters will cancel, and we're left over with kilograms per minute. Instead of A of T, I'm just going to use A. So this will be, and a 15 and a 1,000 can both be divisible by 5, so we get 3A over 200. And the units are kilograms per minute. So we have our incoming rate, which is a constant 0.45 kilograms every minute that passes. And then the outgoing rate at which salt is leaving the tank depends on how much amount of salt there is in the tank at any given moment. So that's going to change as time changes. So it's 3A over 200 kilograms per minute for part E. Now part F asks how much salt is in the tank after 10 minutes. And this part, there are actually kind of two subparts. One is to find how much amount of salt, how many kilograms of salt there are in the tank at any given time, and then to plug in 10 minutes into that function that we get. And the way we're going to start this is writing a differential equation that models this system, that models this situation. So we have dA dt, the rate at which the number of kilograms of salt in the tank are changing, is going to be the rate at which salt is entering the tank minus the rate at which salt is leaving the tank. In other words, rate in minus rate out. So this is exactly what we were saying our differential equation model is going to be for these kind of mixing problems. Well, the rate in and rate out we figured out in parts D and E. The rate in was 0.45 kilograms per minute. The rate out was 3 over 100. You can see it's a differential equation. The function that we're trying to solve for here is a of t, where I'm just writing a of t as just a. But you can see we have that function and we have its derivative over here on the left, so that's a differential equation. Now to solve this differential equation, it turns out we can solve it as a separable differential equation. But first let's get rid of this fraction. It's kind of annoying to have that fraction there. I'm going to multiply both sides through by, whoops, this is supposed to be a 200 on the bottom. I'm going to multiply both sides through by 200. And get 200 dA over dt. 200 times 0.45 is 90. And you have minus 3a. Now, to separate the variables a and t, so a and t are like our y and our x that we're trying to separate. So to separate the a's, we want to move all the a's over to the right, all the t's over to the left. I switched that around. All the a's to the left and the t's to the right. Doesn't really matter, but one side and the other. So we're going to divide that whole 90 minus 3a over to the left. We'll have 200 over 90 minus 3a dA equals, and then move our dt over to the right. Now a mistake some people might make would be to add the 3a over to the left. But then you wouldn't get a function of a times dA. You would get a function of a minus something times dA, which is not exactly the form that we want to be able to finish off our solution to this separable differential equation. We got to have a function of a times dA and then equals a function of t times dt. In this case, the function of t is just 1. All right, let's go ahead and integrate both sides. Now, on the left side, we have 200 is a constant coefficient that can hang around. Then we have ln of the absolute value of 90 minus a. But we're going to have to divide by negative 3. The reason for that is technically you'd have to do a u substitution here, right? Let u equal 90 minus 3a. Then if you let u equal that, the du will be negative 3 dA. So then the negative 3 you can divide over to the other side, so you'll have negative 1/3 du. And that negative 1/3 comes out of the integral. So you end up with an extra negative 1/3. Or you can think by the chain rule, you'd have the derivative of this ln is 1 over the inside, but then times the derivative of the inside, which would be times negative 3. So you have to have this negative 3 to cancel that off. On the right side, integral with respect to t is just a t. Then we have plus c. Let's get rid of that constant. We'll move it over to the right side. So we have ln absolute 90 minus 3a equals negative 3 over 200 t. And here I'm going to be a little bit floppy. What we're going to do is, like we mentioned in a previous video, if we multiply negative 3 over 200 to c, that can be just rewritten as another constant. But here I'm just going to say that the c absorbs that other constant, right? If you do -3/200 times a constant, it's still a constant. So I'm just going to leave that c alone. The c is going to absorb the impact of being multiplied by -3/200. Now we're going to apply the exponential to both sides. We're trying to solve for a. We have absolute value of 90 minus 3a equals e to the let me go ahead. Yeah, that's okay. We'll do it like this. E to the -3/200t plus c. The plus c is up there in the exponent. So we can't say that the c absorbs the exponential. It will, but you have to make sure to follow the rules here. So the exponential would apply to both of these terms right here. So we got to leave the plus c up on the top until we've broken it up so that this plus inside the exponential will turn into multiplication outside a couple of exponentials. So we got to make sure to follow those exponential rules still. We have 90 minus 3a equals plus or minus. Here's where I'm going to break the exponential up into e to the c times e to the -3/200 times t. That way we can rope the plus or minus e to the c into a new letter we'll just call k. My screen was getting excited, flashing on and off. All right, and now we're still solving for a. So what we'll do is we'll subtract the 90 and then divide through by 3, -3. Then a couple of steps. So subtract 90. And then divide by -3. -90 divided by -3 is positive 30. And then here we're going to be, again, a little bit sloppy. We're going to say k divided by -3. That's just going to absorb the divided by -3. So I'm just going to leave it as plus k e to the -3/200t. So there are lots of ways that you can handle these constants. You can be very particular and create a new constant every single time. But you can write C1, C2, C3 if you wanted to. So long story short though, we've got a of t now. I'm going to write a of t equals 30 plus k times e to the -3/200t. So this is an equation that models the amount of salt that we have in the tank over time t. The only problem is that we don't know what k is equal to. And we can figure out k by knowing how much salt there is in the tank at the very beginning, by knowing what our initial condition is. Well, it looks like from part A we said that there were 10 kilograms of salt in the tank initially. Let's use that to figure out what k is. We're going to use that to find k. Or we will try, technology willing. Let me blow on my laptop for good luck. Ah, it came back. Let's see if it has anything on it. Let me blow on it some more. It's overheating with all these solving of mixing problems. My goodness. Let's see if we can finish this off. Find k. Come on, you can do it. All right. So we're going to find k by knowing that the initial number of kilograms of salt in the tank is 10 kilograms of salt. It's erasing as I go. Boy, this is fun. Well, if we use our amount of stuff in the tank function so far, we have 30 plus k times e to the negative 3 over 200 times 0 would equal 10. Now if you solve that for k, you're going to get negative 20. Right, because you'll just get e to the 0, which is 1, so this becomes k, and then you subtract 30 over and you get k equals negative 20. So the amount of salt in the tank over time is 30 minus 20 e to the negative 3 over 200 t. Now we can finally use that to figure out how much salt there is in the tank after 10 minutes. So at this point we know how much salt there is going to be in the tank at any time. We can just plug in any time we want and we'll be able to get the amount of salt in the tank. So let's figure out how much salt there is after 10 minutes. And it turns out there's about 12.79 kilograms of salt. Yes, it finally drew it. Okay, good. Whew. Computer just barely made it through this problem. Okay, so thank you for watching, and see you next time.